Okay, so we're getting into chapter 5. We're finally getting into force and Newton's laws. So we'll just get right into it. Um, so Newton's first law, we see down here is worded kind of funnily, if you, well, if that's a word. And it says, if no force acts on a body, the body's velocity cannot change. That is, the body cannot accelerate. The more classical definition of that is if an object is in motion or at rest, it tends to stay in motion at rest/rest unless acted upon by an outside force, meaning something will continue doing what it's doing forever until something outside of its body affects it in a way. So if you shoot a bullet, it will technically go forever until it is acted upon by an outside force. Now we know that if we go outside right now, there are plenty of outside forces that are going to act on it, right? You have air resistance that's going to slow the object down, and then you have gravity, which is going to eventually pull it into the ground. If you eliminated just those two, it's going to virtually go forever. If it's going to go into space and continue on until it collides with something. So we're going to get into some of these other things like frictionless surface, etc. Some of the characteristics of this is that force is registered in newtons, and you have the breakdown of what a newton is. It's 1 kilogram meters per second squared. So this is another good unit analysis thing. So if you get this unit analysis, and I think am I on the pen? Yeah, okay. So it forced me to upgrade to Office. I've been using Office 2010 for a long, long time. Now I'm using this 365, and it has different buttons, and apparently they've eliminated the shortcuts or something. If anybody knows what they are, please let me know, because I can't find the dumb shortcuts anywhere. Any case, the Newton. So it's 1 kilogram per meter times meters per second squared. So basically, it's a mass times an acceleration. So when you are looking at a problem, you can do unit analysis by looking at what the units are. And if you have just so happen to have a mass that is suddenly multiplied by an acceleration, well, you've created a force in whatever you're doing. So it's a good idea to look at the units and to figure out what's going on, because sometimes that happens. Sometimes you're doing an equation and you're trying to figure it out, and you do something like this where you multiply two things and you don't actually realize that you've created a force. And this may matter later in the problem or depending on what you're doing. So by knowing the breakdown of what a newton is, that's going to help you when you do the equations. So acceleration of a mass proportional to the exerted force. We still know, no, I guess this is new for this chapter. Forces are vectors, so they have a magnitude and a direction. And again, this is just stating more what I said before about Newton's first law. Inertial frames. So we get into frames of reference, and this gets into like relativity and some other things. So depending on where your frame of reference is, you may see something acting differently. So if you ever try to measure something on the ground, if you lay a meter stick, you know a meter stick is straight, right? If you lay it on the ground, it lays parallel to the ground. So you would say to yourself, okay, the ground is flat, right? But this is only over short distances. You can't actually get the curvature of the earth until you get to a large enough distance between 2 points. So if you had a meter stick that was long enough and also rigid enough, because just a regular wooden meter stick is just going to curve to the same curvature the earth has, because of how pliable it is. If you got something rigid enough that would retain its shape, it would eventually just be floating in the air on both ends. The example they're given here is a frictionless puck is pushed from the North Pole. So basically it's pushed from the North Pole here straight down. And what they're saying is, if you're standing right there and you're the one that pushed it, you're going to see it just gliding over a flat surface, right? But if you looked at it over a long enough distance and, from the right frame, you're going to see that it's actually not going in a flat line. It's going in this curved line down here. So technically, because something is no longer moving in a linear motion, it's moving in a circular motion, technically it's accelerating, right? We learned that in the last chapter. The speed doesn't have to change per se, but in this vector notation, you're changing the direction it's going in. Therefore, it is technically accelerating. So in one frame of reference, it's accelerating. In another, where you're just standing there on the ground watching it slide by, it's not accelerating. It's moving at a constant velocity. So that's basically what this is trying to say. And this may not be so important right now, but it will be important later. So there is a definition of mass, and you get some kind of interesting, like a conceptually weird thought process when you start to ask yourself things like, what is actually mass? We know mass from the real world, right? So you pick up your phone or whatever, you can feel that it has weight to it. It has a size, a volume. So intuitively, we're like, that's mass. I eat too much cake, I gain mass, right? We don't like that. So, but you start to ask yourself, what actually is mass? You get into like some weird, sort of almost philosophical questions that original scientists and stuff used to ask themselves. And we need ways of classifying these things so that we can actually apply it to equations, to a thought process, a conceptual idea, whatever. So, for the purposes of definition, we have these definitions here. Mass is a measure of a body's resistance to a change in motion. Right? So, easiest way to picture this, you have a rock on the ground, you go to push the rock with your finger, it's not too hard to move. Then you have the boulder the size of a house on the ground. You go to try to move it with your finger. It doesn't want to move, right? Because it has a much greater mass. So, but we have to be careful with that definition because that also falls within like weight, right? So we have weight here. And you could say the same thing about a small rock versus a large boulder, that one has a much greater weight than the other one. But they're not the same thing. And you have to be very careful, especially on tests and quizzes, whether it's in here or in the future, engineering, physics, etc. You have to be very careful the way the question's worded. Because if it says, so and so has a weight of blah, 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 that means they have already multiplied this by mg. So your weight actually equals your mass times your gravity. So do not take weight as given mass. What you're going to end up doing if you do that, if you say, a weight was given whatever, and remember that hopefully it clicks in your mind that if it says a weight is given, then it would have to be, again, this is a mass, this is an acceleration, so this is going to be kilograms meters per second squared, right? So again, this is our original definition of newtons. So if it gives you a weight, it must be in newtons. So if something says it has a weight of 5, don't take that to be kilograms. The weight is not kilograms. The weight is the kilograms multiplied by gravity. So if you take that, you're going to end up accidentally multiplying by gravity twice. So be very careful with that, how that's worded. Density, we know, is mass divided by volume. And in size, they're mostly referring to just volume here. But and then these are conceptually okay, but you don't necessarily need these things to get through a problem, right? So mass is inversely proportional to acceleration. That may not be inherently useful as you go through this, but maybe later on you'll understand it better. And then you have we're applying a force. So in this example, it's like you put your hand on a rock and you're pushing it with 8 newtons of force. And you're applying this to different masses, right? So again, using the boulder analogy, if this boulder is 1 kilogram versus 2 kilograms, and we apply the same amount of force, it results in a different acceleration. So that should be, again, very intuitive. We've all tried to push things. We know that as things get heavier, they are harder to push. The mass is greater. There's some other things involved in there like friction. Obviously, if you try to push a refrigerator, it's going to be difficult. But if that refrigerator is on wheels, right, that's going to make it easier. If that refrigerator is on a frozen lake, the coefficient of friction is lower. It's going to be easier. But for right now, just ignore those things and stick with the idea of a larger mass is going to take more force to push at the same speed as something with smaller mass. Okay, Newton's second law. Newton's second law we generally refer to not so much in words like the original first law, but more just F equals ma. And it's very important to note this net, right? So the net, you have to be careful because you can have equal forces on something, and if they are equal, that results in no acceleration. And we'll get to more of that in a minute. But basically, what this is saying is you, just like we did before, you're separating the problems into the three axes if it's three-dimensional, and you're going to add them up. So you want to look at all the forces in the x, the y, the z, and then you're going to add them up accordingly in just those axes. So that's going to tell you whether something's moving or not. So I'm going to just move along here because we'll get to some examples of this. So again, if a net force on something is 0, it's not moving. And I'll try to make a little example here, I guess. See, if we have like just a block, say, and it's on some kind of ice, and you push it. So now it's moving in this direction at some velocity. Now you can see it's just sliding along. I'm going to draw a little like animated motion, but set it farther away. And you can see that it's just moving along this direction. We're going to say that it's on ice. We're going to ignore friction. We're going to say the friction is 0. So remember, by Newton's first law, the friction is 0. Again, we're in baby physics, so air resistance is 0, friction is 0, nothing is acting on this thing at all. Whatever initial force we applied to it, and whatever velocity it ended up at, it's going to slide that way forever, unless something comes in contact with it. Now, let's say that you apply another force in this direction. And we'll say it's like 5 newtons. When you apply this force, what's it going to do? It's going to deaccelerate this block. So then if you came on the other side and you applied another 5 newtons, then you've basically canceled this out. Now you're applying forces to both sides, but it's no longer causing an acceleration or a deacceleration. So you're back to square one. Even though there's forces on both sides, now this thing's continuing to slide this direction forever. Okay, so again, this is a basic example. We're going to get to more of this in some of the future slides. Again, down here, so the SI unit for force is newtons. So anytime, again, that you want to do SI units for force, it's newtons. If you use something like dynes, that is usually used for engineers, which is going to be almost all you guys. So dynes are used a lot by engineers. Engineers use a lot of weird ones. You have these down here. It's slugs and dynes and all this stuff. We don't use this stuff in physics. So you can see the mass is the slug and the dyne is the force. But anyway, we're not going to use anything except the SI units for the physics classes. Okay, so this kind of goes back to what I was basically drawing in the last slide. So you have a horizontal force, and there's some force acted upon it. So now it's going to be moving in a certain direction. What we're doing here is it's called free body diagrams, and these are really important. You should also be, if you're in the 180 lab, you should be approaching the lab where we're going to use a box. I haven't looked at the syllabus. The syllabus is a little goofy this semester because of all the online stuff and it's messed up. But you're going to have a coefficient of friction lab, and it's going to be a box on an inclined plane, and we're going to do a lot of this stuff, and you're going to be able to technically see it in person, although I know 95% of you have already chosen to do this stuff online, so you're not going to do it in person. But when you do that lab, you're going to see more of this stuff. So if you get lost in the lab, please come back to this section, and it should be useful to you. So when we do this, like I said, we want to do a free body diagram. What is a free body diagram? It's something that's labeled. You have your body that you're using, and then you want to draw all the forces acting on it. Once you do this, it's going to give you a better idea of the situation that's happening. Is the thing accelerating? Is the thing moving? Which way is it moving? What's happening? So if you draw just this puck and there's no arrows on it, that means it's not doing anything. It's just sitting there. So if we applied a force to it in one direction, this is a singular force applied to this, this thing must move in the positive x direction. Now you say to yourself, okay, well, what if the force wasn't great enough? If this is a ice hockey puck on the ground, what if the force isn't great enough to move it? What if you just, an ant came up to this thing and started pushing on it? An ant's not going to be able to move a hockey puck laying on the ground. The thing is, we're going by the force diagram. So according to this, the only force acting on this is being applied in this direction. So this automatically tells us that there is no friction. Friction is going to be a force acting against the movement of something, and that would have to be a second arrow. So in this case, with no information given whatsoever, I know that this must be a frictionless surface, and a force is being applied to it, which is going to result in this thing moving. Okay, so you still have basically what I explained. So here, now we can see that a force is in the opposing direction. So a good example of this, we could just say this is friction, right? So friction is always in the opposite direction of something you're applying a force to. If you try to, again, using the refrigerator, you push on one side of the refrigerator, the friction is going to work in the opposite direction. And it is going to be equal to the amount of force you apply until the thing moves, right? So the fridge, along with the coefficient of friction, is pushing back on you with the same amount of force as you're pushing on it until it gives. Once you start pushing the fridge forward, then you have applied more force than the friction is applying on the opposite side. So in this case, because they're vectors again, you can see that the length of this vector is shorter than this one. Therefore, again, we must be applying more force than the opposing force of friction on the opposite way. Therefore, this thing is still moving. And again, we know all this just by looking at these arrows. If you start to get forces that aren't purely in the x direction, then you're going to have to break them up into their components. So some force is being applied in this direction. We'll say that's 45 degrees. So it's equally in the x and the y. So the total magnitude of this vector is not purely being applied and can't be subtracted from this second force going in the opposite direction. We would have to take the component form of that and then subtract it from this. So again, the free body diagram, you can get rid of the puck and everything else, and this is what you see. This is being applied, this is being applied. Basically, the slide is long-windedly talking about external and internal forces. An internal force, this is the equivalent of being able to pull yourself up by your bootstraps, to use the old phrase. Obviously, it's impossible that you can pull hard enough on your shoes that you're going to come off the ground. This is what you call like an internal force. The external forces would be something hitting you and then moving you in another way. We're going to deal with mostly external forces for this. For the free body diagram, all you're concerned about is the external forces. Okay, so here's kind of like an example. We have this figure, and we have a bunch of forces. They're acting on something. Doesn't matter what it is. Could be another ice hockey puck. Could be a car. Could be you. And it's going to ask these different questions. So it's asking, in each situation, does the acceleration A of the object have an x component? Does it have a y component? In each situation, give the direction of the acceleration by naming the quadrant or the direction along the axis. So again, these things we can look at them pretty easily. You don't need paper and pen and calculator and all this stuff. So we can see that basically over here we have, in the x direction, 3 plus 2. So this is 5. So you have 5 moving in this direction. this side, we can see there's 5 moving in that direction. So what does that tell us? In the x direction, this thing's not moving, or at least it isn't accelerating. Again, you have to be very careful with the terminology because this thing could be moving at a constant velocity in either direction. When you say that the net force on it is 0, it simply means it's not accelerating. It doesn't mean that it's not moving. So even I just slipped on that. You got to be careful with the terminology. Okay, so we use the y. So the y, you have 7 moving up, 4 moving down. So this just becomes 7 minus 4, right? So you're moving a net positive 3 newtons in the upwards direction. So this thing is accelerating in the positive y direction. Hopefully you get the gist of it. You can see what's going on here. We have 2 and 3, so this is moving in the positive x direction. Then you have 2 and 4 moving in the negative, so we add those together, right? So this is 6, positive is 6, so in the y direction, it's moving nowhere. Again, same thing, 4 and 3 is 7, this is 6, it's moving in the negative y direction, 5 is greater than 4, it's moving the positive x, and so on. You pretty much get the idea. It's the same thing here. Okay, gravitational force. Gravitational force happens with all objects of mass. So when we think of gravitational force and we think of G, that's in relation to Earth. That is purely Earth. Obviously, if you went to the moon, you wouldn't use G, right? The gravity is not the same on the moon because it has less mass. Now, if you were to go in space and you were, we'll say, 100 million miles away from any planets, and it was just you in a car, the car has a much greater mass than you. So eventually, you would be orbiting the car. If you're not orbiting, you don't have enough velocity to go around the car, and eventually you would just fall into the car. The car's gravity would be greater and would draw you towards it. Again, I'm trying not to get too much into that because those are some later sections. We'll get into orbits and rockets and stuff eventually. But the thing you need to know is G is in relation to the Earth. It's also more specifically related to the surface of the Earth. So that value of 9.81 is only in relation to the surface of the Earth. Now, most of the time, we are not going to get far enough away from the Earth for this to change. If you're talking about the surface of the Earth, you're talking about within the atmosphere of the Earth, generally like 60 miles or so, maybe 100 kilometers above the Earth's surface. You're still well within the bounds of the 9.81. It's only going to start reducing this number once you get far enough above it. And at least for this class, we don't deal with those kind of distances from Earth. So, but again, we're talking about the forces. So the mass times the constant of gravity gives us the force of gravity. And we know it's a vector. We know they're acting in the same direction. That gives us direction pointed towards the Earth. So weight, same deal. We went over this already. So weight is just the mass times the gravity. And that gives you the force of gravity, right? Again, it's always pointed towards the Earth. If the Earth is a circle, it's always pointed towards the surface. So you're always perpendicular to the surface, wherever that is. If it's just a flat, close-up version, obviously, you know it's already down. But just to give you the idea of the frames of reference, as you look at different places, it's going to change it. And here's just a breakdown that we're acting the net forces in the y direction. You have mass times acceleration. And then we're saying that the weight minus the force of gravity. And then you can just get the weight actually equals the force of gravity. Because we already know that weight equals mass times gravity. The force of gravity equals mass times gravity. Therefore, these things equal each other, right? So weight is mass times gravity. Okay, so this is probably a more difficult concept to grasp just because throughout your whole life, no one has ever mentioned something called normal force. You're going, what the heck is normal force, right? You're going to get a lot of normal forces in the book and the problems, etc. What a normal force is, it's sort of two things. One, it was something that was simply devised to make the system of forces that we as human beings work, right? So we know that gravity's pulling down on this block. Then how can we say that no other force is being applied to this because it's not moving anywhere in the y direction? This thing is just sitting on the table. So we know that the forces have to balance. So what we say is the force of the table is applying a force to this block that is equal to the force of gravity pulling it down. This is why it doesn't move. And you can kind of get more into it if you're saying, okay, this is just some contrived notion of human beings. You can get more into it and say that at the atomic level, the atoms are actually repelling this in such a way that they are applying the force that is equal to the gravity. Obviously, if we keep increasing the mass of this block and that increases weight, that the weight goes heavier and heavier, eventually it will overcome the normal force that can be supplied by this table. If we get something that's large enough and heavy enough, it's going to fall through the table, right? It's just going to break it and go right through it. So that's how you can kind of justify in your mind that this is giving an equal force. This is similar to what I was saying with the fridge, right? If this is a fridge and this is an overhead view, and you're pushing on it, and that's you, and that's your tiny legs. You have really long arms, don't ask. So if you're pushing on the block this way, then the force of friction is pushing on the block this way. So it's the same as the table is pushing back on you, right? So eventually, if you push hard enough, you can overcome the force that's pushing back on you, which is the friction. So the same thing for the table. If the table's the force that's applied to it is great enough, whether it's mass added or just a force being exerted from the vertical direction, then it's going to overcome the normal. It's going to overcome the normal forces pushing on this table. So hopefully that makes sense. So when things aren't moving and they're sitting still, there's always a normal force acting on it. The normal force must be pushing equally back on it if it's not accelerating in a direction. And again, that's always perpendicular to the surface. So again, just real quick while I think about it. If you have something in this direction and there's a block on it, because this will become more relevant again when you do the inclined plane for the lab, and we'll also do some examples at the end of this. I'm kind of getting ahead of myself, but the force of gravity is always pulling down. So in this case, such as in the lab, the ground is in this direction, and that should be straighter. I just can't do it with this goofy pen. The plane itself is going in this direction. So the force, the normal force that's acting on this is perpendicular to this plane. So it's actually, normal force is acting like this. Because again, you want to tell yourself, is this thing moving through this plane? And it's not. It's sitting on top of it. Therefore, the normal force must be acting against it. And then you say, okay, well, there must be an equal force moving this direction. And if I make it equal, I'd have to extend the tail to be as long as this one. But there must be an equal force pushing this way. That comes in the components of this guy. So you're going to have a component that is in the x and the y of this gravity pulling down. And we'll get into that more. Okay. So again, this is adding up the forces. We kind of already went over this. In the physics, especially 180 physics, they like to use a lot of these elevators, right? I guess physicists are just fascinated by elevators. So they're saying if the magnitude of the normal force greater than, less than, or equal to mg if the block and the table are in an elevator moving upward. So if it's moving upward at a constant speed, that means the forces are equal. This thing is just moving along. It's not accelerating, right? So that means the forces have to be equal. When you start increasing the speed, that means there's an acceleration. If you're on an elevator, when it immediately starts and when it immediately stops, it has to accelerate and deaccelerate. In these times, it's going to change the measured weight of something. So if you put a scale in an elevator and you stand on it and then you send the elevator up, the scale is going to read heavier than it should, right? But then once you get moving at a constant speed, the weight that it reads is going to be what it should be. It's going to be your actual weight. So again, there's some more examples of this we'll get into. And then this is explained here. The frictional force. So again, I've explained this kind of already quite a bit. You have the frictional force. We usually draw it parallel to the surface and usually directly on the surface. So it's important to draw your forces to keep track of them. Because if you have several forces that are acting on this, you don't want to get them mixed up. So by drawing it here and then drawing it along the surface, this helps you remember. You can also draw it, I'll draw it a lot of times on the outside of the object. So I'll draw it like this and then draw it backwards. I usually do it this way. That helps you to remember that it's going opposite of this. Sometimes it's also going to be drawn this way, right? So you can put it against the object. You can kind of envision it being at the front of the object, moving if you want. They all mean the same thing. Just kind of use the version that sits in your mind best so that you understand which direction the friction's being applied. Okay, tension force. So tension force is, again, a whole other bunch of problems you're going to encounter in physics, and it has to do with blocks on ropes, right? So if you have a block and you have some rope holding it up, and we'll say it's just tied to some bar, the rope feels a tension. And we just label that as T. It feels some tension. So the block, again, because we usually use center of mass for objects, is being pulled down by mg. But it's not moving anywhere, right? So there must be a force countering this. So in this case, we say that the force countering it, much like the normal force, is in this case tension. So tension is then countering this force going the opposite direction. So that means this thing is not accelerating in either direction. It's just hanging there. It's not moving. Again, these terms are going to be used a lot, especially in 180. Again, you're going to have to get very far in your academic career before these things start going away. So most of the time, and massless versus mass, they're talking about the rope. The rope, the chain, whatever it's connected by. We usually say it's massless because the problem becomes more complicated when you say it has mass. If I were to cut this here and the rope were to fall, well, it has some mass on it, but then that mass is increasing. So you're going to get into a little bit more variations of you're using your calculus, right? Because you have something that's changing at a constant rate as this rope would fall on it. It would increase the mass as it goes, as the rope begins to fall on the block. So for especially for starting out, we're just going to say that most of the ropes are massless. They are unstretchable because that adds another component. A lot of times we're going to say if there's a pulley, say this is a pulley, and try to make it look more like a pulley. We'll say the rope goes up and over. A lot of times we're just going to say this is frictionless because where these ball bearings are inside here, it's going to create some amount of friction, right? So we'll say it's frictionless, it's massless, it's unstretchable, all these different things just to simplify the problem so you guys can see the fundamentals of what's happening. And again, so a lot of these problems change quite a bit when you say this is a frictionless surface versus there's some friction acting upon this. Right now, we can see that this is acting an equal amount. So the block is basically pulling as hard as the hand is pulling, right? So we're basically saying that mg is equal to the amount of force that this person is applying to this rope. So it's not moving anywhere. and we know that there's no friction technically. So it ends up being a weird situation where you're pulling on a block where it would basically have to move because the mg here is not being multiplied by any kind of coefficient. So if it's frictionless, technically it's going to move. But from the information we're given, tensions are equal, therefore no acceleration, no force is being applied. So now when you put a pulley in it, again, we say the pulleys are frictionless. Now tension's being applied this direction and this direction. So they're no longer in the same direction, but because the pulley's in there, we can equate them to each other. So again, you have to keep that in mind. And then third situation is basically just a pulley and you're pulling down. If you've ever messed with a pulley in real life, you know if you pull this down with a great enough force that is greater than the mg or the weight of this pulling down, that this is going to go up. But the thing we're focused on is the tension of the rope. So they're saying here, it's just looking at C. It's saying, okay, this thing is 75 newtons. Is it equal to, greater than, or less than 75 newtons when the body is moving upward at constant speed? So if it's moving up at constant speed, again, that means there's no acceleration, so there's no force, so it's equal to 75 newtons. Increasing speed equals acceleration, right? So, and then decreasing also is acceleration, it's just deacceleration. So that gives you information to the force being applied, right? It's greater than, it's less than, it's equal to. Okay, so getting into the vectors, I kind of went over this already. When two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. So we'll look at this again. Again, this is more of what I just kind of already said. You have a cantaloupe on a table that's sitting on the earth. So the vector of the cantaloupe, which is labeled by C, so you have the points C and E, stands for cantaloupe and earth. So when we draw the vector from one to the other, you have CE, meaning it starts at cantaloupe, goes to earth, and EC, meaning it starts at earth and goes to cantaloupe. So these forces must be equal to each other because this is not accelerating in any direction, right? And we can look at this for a closer example of something. Again, we're reducing our frame of reference. So now we're just looking at the table. So cantaloupe to table, table to cantaloupe. Again, it must be equal. And they're calling these force pairs, right? Okay, checkpoints. Suppose that the cantaloupe and the last figure are in an elevator, again with the elevators, that begins to accelerate upwards. Do the magnitude of F table to cantaloupe and F cantaloupe to table increase, decrease, or stay the same? Again, they must increase because you're accelerating now. Again, the frames of reference. If you have an elevator and you have the table inside and you have the cantaloupe on it, if this thing starts suddenly going upward, the cantaloupe still doesn't fall through the table, even though there's a greater force being applied to this. So, how can I do this? Can I write over here? No. I did things I didn't want to do. If I draw a second version of this, and we'll say this one isn't moving, it's just sitting there. This one has suddenly started to accelerate and move upward. And they're saying, what do these two vectors do? So you have one vector from the cantaloupe, which is the center of this, pulling downward. And then you have the vector from the table moving upward. So we're going to say this is the table, this is the cantaloupe. I can draw this. And these things have to equal each other because this thing's not going through the table, right? If we look at it where it's just sitting still, it's actually the exact same situation. If you are inside the elevator, from your perspective, it's a cantaloupe on a table. And then when it's not moving, guess what? It's still a cantaloupe on a table. So only from the outside do you see this thing start moving upwards. So from the inside, if we draw the vectors again, you have the cantaloupe coming down, and then the table going up. And if you noticed, I made the vector shorter, right? Because it's not accelerating, or it's not accelerating upwards, so we're not adding to the force. Here, this is just basically mg pulling down. This is mg plus the acceleration of the elevator. So the vectors must increase, but again, it doesn't fall through the table, so they must be equal. The table is pushing on it just as much as the cantaloupe is. So hopefully that makes sense. So here again, we have the pulleys, only now we're adding the mass to the block. And again, they like to use these a lot. They use like the masses of multiple blocks. And usually there's a large block, which is labeled with capital M, and there's a small block labeled with lowercase m. So you got to be careful with this, and you have to keep track of the big M's and the little m's. Because when you go to do these in a problem, you're going to have to pay attention to it. If you have really bad handwriting and your m's kind of look like this or something, and you can't tell the big one from the little one, what I would do is instead of using capital M and lowercase m, maybe do M1, M2. But if you're confident you can make a big one and a small one, then go for it. But just make sure you can tell them apart, however you label them. So it says a block of mass 3.3 kilograms connected by cord and pulley to a hanging block of mass 2.1 kilograms. So this one's 2.1, this one's 3.3. These are masses. Slides across a frictionless surface. So it's telling you it's frictionless, therefore it must be pulling on it. And then basically you can calculate the velocity at which it's moving by the masses. And it's telling you here, again, that in these directions, the normal force, again, the F of the N is always denoted by usually the N because it's normal force. That's pushing off this table or whatever it is. The block is pulling down with gravity, right? So these must equal each other. It's not accelerating up or down. It's not actually moving at all in the y direction, so these have to equal each other. So then you have the tensions on the rope. The tensions on the rope equal each other, but then you have the force of gravity also applied to this thing. So it's pulling this block down, and then that's going to pull this block forward. So again, it's basically just, this is a free body diagram of exactly what I just explained. You have a force in the positive y, a force in the negative y, denoted by the gravity, and then denoted by the normal force. These are equivalent to each other, so there's no acceleration applied in the y. We know the block is moving to the right in the positive x, therefore there's an acceleration being applied. Also, the force of gravity is pulling the second block down, therefore there's an acceleration in that direction. So this is basically the free body diagram for big M and the free body diagram for the little m. So you would have two separate free body diagrams. And if we go back to this, you could actually just apply it to this depending on your neatness of the page you have and how you want to draw it. But you can apply it to both. But you're going to have to get really used to doing these free body diagrams. It's a great way to learn what's going on and then to model the system. Because remember, the physics to any of these problems comes in when you're doing this stuff. When you're making the free body diagram, then that's where the physics is. The physics is not in you have an equation out here and you have to do the algebra or calculus or whatever and get a numerical answer. That's just math. The physics comes in modeling the situation and setting up that equation. Okay, so we have the tension is then equal to the mass times the acceleration. And we leave this specifically as acceleration because it depends, like we had the previous two blocks when we use big M. So we have same thing here. It goes like this. You have little m and then big M. So big M is moving in the x direction, so it is some acceleration is being applied to it, but we don't want to say it's gravity. Little m has a gravity applied to it. So if you take the tension, which was that shorter vector upwards, and then you subtract it from mg, the bigger vector, then it doesn't cancel out. You're left with some acceleration from this mg, right? So they're saying you can combine these, and again, this is where it gets kind of messy if your m's are not differentiated between the two. You got little m, big M. So make sure you can differentiate between those two. Make sure your handwriting is good, or you change it to 1, sub 2. And now they're just giving you values. Plugging in the value of acceleration is 3.8. We can say the tension is 13 newtons. And this is a very important part also of physics. So anytime you get to the end of an answer, you should ask yourself, whether it's a test, a quiz, the lab, an experiment, you're doing homework problems or whatever, say, does this make sense? And if you're not sure if it makes sense, compare it to something else. So if you had something like these blocks, and to make it more real world friendly, because we're Americans and we use pounds and whatever, if you know that this is 5 pounds and this is 10 pounds, and then you say it's moving downward with a force of 50,000 newtons, you're familiar with what the pounds. You know this is heavier than this, therefore it's going to pull it downward, right? So if you say that it's moving downward with the force of 50,000 newtons, you're not familiar with this number, but something should probably tell you that this number is a little crazy, right? This seems excessively high. So if you had to, you could Google like how much 50,000 newtons of force is. I don't know. This might be the equivalent of like a large payload rocket taking off from the surface of the Earth or something. This is a lot of force, right? So something intuitively should tell you that, hey, this doesn't make sense. The same as if I were to take something the size of a Rubik's Cube and solve for the volume of it. And I'm like, when I get to my end answer, I say, okay, it's 50 cubic meters, right? 50 cubic meters is going to be the size of a large room. This is not the size of something smaller like a Rubik's Cube. So something should tell you, oops, I did something wrong. I better go back and look at this. And you should always be looking at this. Same thing with velocities. Again, we're used to miles per hour, but you're going to get meters per second in this. Just try to convert it to real world things to see if it makes sense. Just look at your end result and see if it matches. Okay, so this is very similar to the lab. You have an inclined plane, you have a block on it. For one part of the lab, you are going to use a spring pulley system to pull this up. And then we have the free body diagram drawn here, right? So I stated this in the other slide, but you can see it probably a little bit clearer in here, and it's not using my messy writing. So you have the force of gravity pulling downwards. And just like I stated before, the normal force is perpendicular to this surface. So if you change the normal force is going to be about like so. If I change the angle of this and make it like this, I have to adjust my normal force to that angle, right? So it's going to change depending on the angle of the plane. So again, when you go to figure out the components, because we don't deal with anything in this weird place between X and Y, we make things as simple as possible. We break them down into purely X, purely Y. Then we know we can add them, subtract them, do what we want, and it's easier to understand. So this portion here, you're going to have to break down into the X and the Y. And you want to make sure that you know what's going on with the geometry of this. So you can mess around with this lot and make all kinds of angles. You want to do what's easiest for you, though. So a lot of times you're going to be given some angle in a problem typical to this. Only problem is it's going to be labeled just like this one. It's going to say theta. You're not going to know what it is. So what they're basically saying is that remember your geometry, and this is going to be 90 degrees minus theta. So you know what this is. And then if we say this is phi, it's some other angle. So these are two different angles, right? If it happens to be a 45-degree angle, then it's the same angle, but we don't know that because no information's been given. So when we look at this, if you say that then this is 90 minus theta, then if you draw a line here so that this is actually a right angle between these two, then this angle must also be theta. So we've taken essentially this triangle, rotated it over, and transposed it onto this guy. This is what you're doing over here, right? You're going to have to do this problem a lot so you get used to these angles. If you don't understand it, definitely go through it once, because this is a very typical physics problem. And the thing is, you can get used to it. You can just go like, oh, okay, I've seen this problem before. Theta's here, same thing. Bada boom, bada bing. This is sine, this is cosine. I already got everything. I don't have to do any geometry. I know everything. Problem is that the situation changes slightly, and you don't know where it came from. So on your own, go through the geometry and make sure you understand what's happening, and that if we change the angles, we change the situation, you can still do it on your own. It's very important. So again, going through the problems, you want to go through the problems and make sure you understand them. Okay, so again, this just kind of goes through the geometry. So from this, we're basically pulling our coordinate system. We're making it this direction. We're saying x is in this direction, y is in this direction. If you go through this, you're basically going to say, you're going to come to the conclusion that your sine theta component is going to be in this direction. You go this direction. You're going to have a cosine theta component. And actually, I didn't even notice it's drawn down here, so I'm not even going to draw it. So when you draw this, this is just your mg, which is that force that is pulling downward on this, split up in components. And you say to yourself, well, this is in the y direction. Why do I need to split it up in components? It's just in the y. This is one of those cases where you're reorienting the coordinate system. So the coordinate system, naturally you think of as x and y. In this case, everything's moving along this plane. So what we want to do is we want to change the coordinate system. And just to make it easier, we're going to make this x and this y. So hopefully, that was awful. This is so hard to control. Hopefully this makes sense. This is your normal x and y. This is now, we've rotated this to match the angle that's here. So we've rotated it, and now this is the x and this is the y. So if we do that, all of a sudden the forces that are acting on this, I'll draw it over here. So now it's going this direction and it's going this direction. Now we have a normal force acting in this direction. And then we have the cord pulling on the box. We'll say that's some force. So it's some force of a pull acting in this direction. And now all of a sudden the mg is acting in this direction. And hopefully that makes sense, because we've just taken this bit and we've rotated it so that the box is on an x plane. So now you can see that this is no longer in just the y. So this is why we break this piece up into components. And again, you get the mg cos, where it comes from, and the mg sine down here. Those are the pieces you're going to use. Again, it's a problem you're going to want to go through a couple times on your own. Okay, and then that's just the summary, and that's it. I will try to get to some problems later in the week so that you have a better idea what's going on. Like always, just email me if you have a question.